since everybody's here, let's get started. First, I will talk about our final exam. The final exam will cover all the subject we have covered so far. So that translates to 6 chapters plus another 6 chapters. So that will be a final exam. Chapter 1 through 6, that will be the midterm. 6 chapters before the midterm, and 6 more chapters after the midterm. And I will post the final exam this weekend. So you have Monday and Tuesday to work on it. So 2 days. The only limit is 2-hour limits. So it's obviously another, you can open book, but the 2-hour limit. So that's the only limit. You can work on it Monday and Tuesday anytime. Just pick a period where you know for sure you can sit in front of your computer for 2 hours straight without interruptions. That's all you need to. So the test format is identical to our midterm. So if everybody did the midterm, so it will be no surprise. Because it's a 2-hour exam, I will have probably double the amount of test problems, but it will be exactly same style. Everything we covered is on the on the test. So if you go throughout the material, read the textbook, I don't think you should have any problem. So that will be our final exam. I will post the exam on Canvas this weekend. You have 2 days, Monday and Tuesday, to work on it. So with that taken care of, any questions with our final exam before we move on to our last chapter?
Do we have an exam review?
Yes. I'm sorry,
okay.
I just turned on the speaker. Exam is
what'd you say?
I just turned on the speaker. I didn't got the question.
Oh, well, I was going to ask if we had like an exam review that we can do.
Exam review, it will be right now. I don't usually do a review. Basically, everything we covered is on there.
Okay.
Yeah. It's the subject is simple and straightforward. So the first half will be the sensors and the concept of controls, different type of control. The second half will be pretty much the actuators, the controller, the PID controllers, and of course today's topic is the tuning. So every test problem is related on those material.
Okay.
So yes, very good. So as far as the sections go, all the sections we covered pretty much all the sections. I don't think we missed any sections. Maybe a little bit on chapter 8, the PLCs. We didn't cover PLC. That's maybe the only section we didn't cover. Section 5 of chapter 8. But other than that, because we have a separate class, everybody needs to take a PLC class. So that is not covered. Everything else, the basic concept of ladder diagram, everything else we covered. The discrete process analog controller.
Can we get a copy of the midterm somehow?
Just a copy of midterm. That's a good question. I will study that, see if I can post the midterm. Yeah, that's something I will. Yeah, that's good. Copy of midterm. I will study about it. If I figure out a way, let you know by Wednesday.
Okay, thank you.
That's a good question, Joe, because the final test problems, some of them are related to the first test. Yeah, you don't want to make the same mistake twice.
Nope.
Oh, yeah. All right, great. Let's move right on to our last chapter. Last chapter is a controller characteristic. More specifically, we are talking about the PID control. So let's move on to 559. That's last chapter. So introduction about the control. So we will skip all that. And then they also talk about besides the basic PID control, we also have a more complicated control other than the basic PID. The first one will be cascade control. That is not required, not the test problem, but just for you to know, the PID control has a pretty good performance, single loop, but in some real-world applications, that's not enough. So that is what the cascade control is. You have an inner and outer loop. The inner loop will control one process. The set point of inner loop came from the outer loop. This is an example. For example, if you want to control a DC servo, in a DC servo, if I remember correctly, we have an inner loop control the current for the DC motor. The outer loop will control the RPM. So the RPM basically the voltage. So for a DC motor, the outer loop controls the voltage, the inner loop controls the current. The voltage is the RPM. The inner loop controls the current, which is torque. So basically for DC motor control, you have an inner loop control the torque of the DC motor, the outer loop, which is current. Then the outer loop control the RPM of the motor, which is the voltage. So that is a DC, for example, control a DC servo. You have a voltage and current you need to take care of. That's the motor control. So cascade control, that's one way to do it. By the way, the cascade control have two PID controllers. You have a PID controller here, and for the current, and then you have a PID controller here. The outer loop is also a PID controller, control the RPM. So it's a extension of your basic PID controller. So your basic PID controller is a simple one loop, but there is more complications. Another topic the author covered is called the multi-variable. Yes, multi-variable. So some of the control may have multiple sensors. That makes sense. You do not always control things based on single sensor. You may have multiple feedbacks, and then you make a decision, control decision based on multiple inputs. And of course, you potentially have multiple outputs also. So multiple inputs, multiple outputs. That's another subject we didn't touch on. So that will be potentially future studies, or potentially you may encounter when you're working in control area. So that's something we didn't touch on. So we barely touch the minimum basics. So now we move on to today's first topic. Today's first topic will be the quality of control system. That's our first topic for today. The second topic will be the stability of the PID controller. We want our PID controller to be obviously stable. The third topic is the tuning of a PID controller. We will study two proven. First is proven, second is simple tuning method. They all developed by two engineers. Their name is Ziegler-Nichols. So these two tuning methods is named after them. So let's move on to the first topic, the quality of PID control. So here's the definition of quality. The definition of quality is how PID controller behave under disturbances. That means the quality of the PID controller. How does your controller behave if there is disturbances? In our experiment this semester, everybody is working on, there's not much disturbances happening because we have a controlled environment. Indoor environment, we have double layer boxes, so your incubator is very well protected from any disturbances may occur. But in the field, in the real world, a lot of the controller has many disturbances. So what is disturbances? There are three types of disturbances, three different types. The first type of disturbances is called the load variation. For example, Joe works in, that cat food company. I forgot it. What was the company name?
Purina.
Purina, yes, Purina. I buy so many of them, but I just forgot the name. Purina, yes. So when you have load variations, right, you can have different amount of, for example, cold water pumping into the hot water tank. That's called a load variation. Or your load varies with time. So that's is one disturbances. The second disturbances is set point. Set point variation is also disturbances. For example, you want to cook one kind of cat food, one temperature, you change recipes, you change temperatures. That's set point variation. It's also called disturbances. Those two disturbances are actually controlled. Load variation and set point. The third type of disturbances is uncontrolled. It's natural. For example, the outdoor weather, something out of your control. They are all classified as transient. Something you cannot control. It may happen randomly. So that's three different type of disturbances. How the PID will behave? We measure the behavior in three criteria. The first criteria will be the stability of your controller. That's number one. Second will be the deviation. So if there is a disturbances, how far away it will deviate. So if your cooking temperature is 200 degrees, if there is a disturbances, it will vary away from the 200, maybe 5 degrees or 3 degrees above or below. So that's called a deviation. So stability means after the deviation, it will reach 200 again. That's called stability. It will not oscillate. Oscillation will unstable. The last behavior we want to check on is the duration of deviation. So if your controller is off by 3 degrees or 5 degrees, how long it will last? How long the controller will correct that error? That's called duration. So we basically will measure the quality and measured those three factors under three different type of disturbances. So let's move on to the first one called stability. Stability. Your controller need to be stable, obviously. So how do you make a system stable? It's actually a mathematical question. It's a theoretical question. It can be answered with a mathematical equation or with a theory. So this is the theory. For any control loop to be stable, you have to avoid two things from happening. So this is two rules we have to avoid, not to follow, we have to avoid this from happening to make our system stable. Rule number one, the loop gain. Rule number one, the loop gain is larger or equal to 1. That is rule number one. Loop gain should always be smaller than 1, not larger than 1. So loop gain is larger. This is something to avoid, not happen. So when you design, so I will say follow the two rules. Loop gain smaller than 1. Phase shift not equal to 180 degree. So those are the two rules we have to follow. The rules to follow is loop gain smaller than 1. Phase shift not equal to 180 degree. That is the theory of a stable system. So what exactly is loop gain? If you look at the control system, it looks like this. So it's a loop. It's loop. This is your controller. This is your process. The controller will send out the signal, control the process. The process is measured and feed back to the controller. So that's a loop. That's a loop. When we have a loop, potentially we can create unstable conditions. But if the loop gain is smaller than 1, this system will be stable. So that's rule number one. Loop gain should be smaller than 1. Only if loop gain is smaller than 1, we have a stable system. Otherwise, your system is unstable. Let me give you an example of something happens in your daily life when a system became unstable. A lot of you use a microphone, right? You notice when you put your microphone closer and closer to the speaker, at a certain point, the loop gain became larger than 1. What happens when your microphone is closer and closer to the speaker? To a certain point, the loop gain is larger than 1. It became unstable, and a very unpleasant oscillation will happen. So that's what happens. Because the closer your mic to the speaker, the bigger the loop gain, getting closer to 1. When it crosses that threshold of 1, it will start oscillation, and all of a sudden everybody is, alarmed because it's a sound very annoying sound happens. That is for when you make a public speech, you do not hold your mic close to the speaker. Just the loop gain larger than 1 doesn't necessarily causing oscillation or unstable. The second condition is a phase shift equal to 180 degree. That means not only you have a loop gain larger than 1, you have a positive feedback. If the phase shift is 180 degree, whatever happens on the speaker will be positively picked up by your mic. And your mic will look back to the amplifier, make it bigger on the speaker, and speaker will send that sound again. That sound will be positively picked up by your mic, so that will create that loop oscillation. If for some reason it's a negative feedback, then the oscillation will never happen. So basically, those are the two conditions we have to follow if we want a stable system. Condition number 1, loop gain is smaller than 1. Condition number 2, phase shift should be as far away from 180 degree as possible. Not close to 180, away from 180. For example, 90 degree or 0 degree would be a good choice, right? 0 degree would be a good choice. 90 degree, 30 degree, we're all far away from 180 degree. It turned out different frequencies of signals have different frequency shift happens like this. That's a typical phase shift curve. That's a typical loop gain curve. So the loop gain is actually drops as frequency increases for a typical system. And the phase shift also changes with frequency. Notice the 180 degree right here, right? That's 180 degree. So when the phase shift is 180 degrees, let's look at the loop gain. What is the loop gain for this system? You go up right here, 0.5. So that implies this system is stable, right? Because when the loop gain is larger than 1, the phase shift is 140 degree, is away from 180 degree. So there is no oscillation here. When the phase shift is 180 degree, the loop gain is less than 0.5, so less than 1. So that clear the check for those two conditions. So those are the two conditions you need to check to make sure your system is stable. First, loop gain smaller than 1. Second, phase shift away from 180 degree. So this is called a Bode plot of your control system. So when you design the control system, potentially you can create a Bode plot for your control system. And once you have your Bode plot, and then you can check if your system is stable. So for example, this system obviously is stable. This system is stable. That's an example. Determine whether the system is stable. The solution is yes, it is stable. It is stable. It is stable. It is stable under rule 1. It is stable under rule 2. So based on the two rules, this system is stable. So this applies for any loop system, not just PID. So this stable criteria apply for any loop, not just the PID loop. What we are talking about is PID loop. The PID loop is just a loop. So the second subject is not limited to PID control. It applies for any loop. PID is just one type of loop. In the industry or in the engineering area, we have unlimited amount of loops. So if you want to study the stability, those are the two criteria. So applies for PID and applies for any loop. So that's our second topic, is the stability criteria. The first topic is the quality of controllers. Second topic is the stability. The third topic is our last topic. It will be the tuning of a PID controller. So over the PID controller has been invented more than 70 years ago. So it's an old technology. It works really well. It's actually pretty easy to tune. So how do we tune a PID controller? There are many methods. With the experience, we can always use one method called try and error. So we can manually tune it with just try different parameters with experience. So as you gain experience, for example, you have tuned dozens of boilers. You had experience. You just look at the size of the boiler, the kilowatts of the heater. You get an idea the parameters, where the parameters are. So, you can try, and if there is an error, you make some corrections. That's one way to do it. Another way to do it is proposed I guess about 50 years ago, I may be wrong, but 50 years ago, that type of by Ziegler-Nichols. So I will introduce two methods. They propose multiple methods. I will propose the method number one called S-curve method. S-curve method. So we will try to create an S-curve or reaction curve or response curve. It doesn't matter how you call the name. We call response curve, reaction curve, or S-curve. The second method is called the cycling method. We will create not an S-curve. Instead, we will create a. So this is the first method. We create an S-curve. That's a S. Look like a S, like a F. S-curve. The second method is a cycling method. The author do not have a plot. The second method, we will create this. That's the set point. That's the second method. First method, that's the set point. We create S-curve. So that's method number one. That's method two. So let's start with method one. Method one called S-curve. So what we do is we turn on the control system without PID. We just turn it 100% on, just like what we did when we find in the range. So we turn on our controller, and then we will check the process. We find that's when we turn on the controller. We turn on the controller in manual mode, not automatic mode, manual mode. In manual mode, we turn on the controller and then we check the process. In our case, will be temperature. So we will measure the temperature. We noticed after we turn on the controller, the temperature doesn't move at all. So it waited for delay time. There is a delay time. So this is a delay time. We call what we do. We call L. Delay time is L. So when we turn it on, there is a delay, and then we notice temperature start picking up, and then goes flat again. So this is a delay time L, and this will be the capital T, time constant. So basically we measure T and L. So in manual mode, remember this is not automatic mode. That means we turn off the PID control at all. There's no PID control. We just study the process. So we turn on the controller, in manual mode, and we notice the temperature doing this. That's called the S-curve, S-shaped reaction curve. So we measure L, we measure T. T is in seconds, L is in seconds, okay? And then this is what we do. This is how we tune the controller. In the textbook, the author do not have this table, so I will put this on the camera for a little bit longer So you can write that down for your final exam because the textbook do not have this table. So after you find the T and L, T is the time constant, L is the delay time. So what about the PID control? So if it's proportional only, it will be the proportional gain will be T divided L will be the proportional gain. So T divided L will be proportional gain. Integral gain will be 0, derivative gain will be 0 because we are using proportional only. How about the PI control? For PI control, the proportional gain will be 0.9 multiply T divided by L. So that will be the proportional gain. Integral gain will be 0.27 multiply T divided by L squared. How about PID? PID, the proportional gain will be 1.2 multiply T divided L. Integral gain will be 0.6 multiply T divided by L squared. Derivative gain will be 0.6 multiply T. So that's the table we use to calculate the parameters for proportional only, or PI control, or PID control, in case we use all three PID control. So that is how we do the S-curve. For example, let's give you some numbers. Do an example. If the T is 300 seconds, L is 200 seconds. So what is the PID parameter if we use PID control? So it will be 1.2 multiply 300 divided by 200, right? It will equal to 1.2.
Would that be 1.8?
Yeah, 1.8. Yes, 1.8. So the proportional gain will be 1.8. In our controller, we will change to band. What is the band? 1 divided 1.8. The band will be 56%, 56. So gain right, 56 band. How about the KI? KI. Zero point 0.45. But our controller do not use gain. Our controller use time. So 1 divided by 0.45 equal to 2.2 minutes, which is equal to 133 seconds. So the proportional, not proportional, integral time is 133 seconds. 133 seconds. How about last one?
Wait.
Yes, question? So it should be 133 seconds. How about last one? 0.6 multiply T is 300. 180 seconds. So No, I got this wrong. Let's say this. The second. Let's use 300. Not 300. Let me recalculate. 200 multiply 200 divide 300 divide 0.6. 222 seconds. I was wrong. 220. So this is let me redo the example. T equal to 300 seconds. L equal to 200 seconds. KD will equal to 1.8. KI equal to 0.4. No, not 0.45. It's actually divided by KI will equal to 0.6 multiply 200, 300 divided by 200 multiply 200. It equals to 0.0045. So that is Ki. And equal to 2. So the time equal to the reciprocal of this will be 222 seconds. So that makes sense right now. And KD will equal to 0.6 multiply 300, 180 seconds. So this one we change to band. Band will be 56. So band equal to 56. I time equal to 222. D time equal to 180 seconds. So now we got the tuning. This will be our Wednesday's lab. So everybody required to, so is there any questions with this one? Because that will be this Wednesday's lab assignment. On Wednesday, we will measure L, we will measure T. This is the delay. This is the time constant. Once you find both in seconds, you should be able to go through this math. Find Ki, Kd, and Kd. Kd is already in seconds, so that's easy. Kd is a second. Kp is not in band, so we need to take a reciprocal of this, then multiply 100%. So 56. The reciprocal of this is 0.56, so multiply 100. So 56 is the band. And how about the Ki? Ki is that, very little, because 200 multiply 200, 300 divided by 200 by the square. And then you take a reciprocal, that means 222 seconds. So that's the first method of tuning, called the reaction curve. Any questions with our first method, with our Wednesday's lab assignments also? Because our controller will create this nice S-curve when we turn it on in manual mode. So that's the method we're going to use.
So, okay, so the time constant and the delay, how do we set those on our controller?
You measure it, you don't set it, you measure it. This is Yeah. You turn it on in manual mode, then measure how much is the delay, how much it ended. So you
Okay.
notice your temperature will not start moving, and then start moving, then stop moving. Yeah.
Uh-huh.
That's kind of finding the range, but but instead of finding the range, you're finding the time.
Okay.
So the time it started, temperature started moving, and the time ended the moving. That's time constant.
Okay.
So you measure 2 times. After you
All right.
measure those 2 times, you go through this math. Let's go through this math.
Are we going to redo this math on Wednesday? Because I don't know, I'm a little lost on it.
It's a simple, but at first it may be overwhelming, so we will do it again on Wednesday. Yeah.
Okay.
So you will find it so simple after you do it a couple times. Yeah.
Okay.
Yeah. It's so simple. It's the simplest method, tuning PID. Yeah.
Okay. Sounds good.
Second method is called the second method proposed by the same engineer. The two engineers also proposed the second method. The second method will be causing your control system to oscillate. So you turn on the PID control, you just keep increase the KP. You increase KP. What happens if you keep increase the proportional gain? Sooner or later, you find your controller output will oscillate. So when the controller output start to oscillate, you measure the gain. That's called the critical gain. You also measure the period. This is called the critical period. So you measure critical period, which is the TC. You measure the critical gain, which is the KC. The KC is actually the proportional gain, but we do not call it proportional gain because it started oscillating. So we call it a critical gain. So you have a critical gain and a critical period. And then what? This is the table the author has in the textbook. Then you will do the calculation. If it's a proportional only, it will be 0.5 times the critical gain as a proportional gain. For PI control, will be 0.45 multiplied the critical gain. The time will be the critical time divided by 1.2. That will be the integral time. For PID control, it will be 0.6 multiplied critical gain. That will be the gain of the proportional. The integral time will be half the critical time. Derivative time will be 1/8 of the critical time. So let's do one more example before we end today's lecture. If I'm tuning my controller and I find the critical gain is 5. The critical period is 200 seconds. What will be the PID control parameter? Kp equal to 0.6 multiply Kc equal to 3. So that's the critical gain. And the band will be 33%. So band will be 33 because that's a 1 over equals 0.33. And then you multiply that by 100, you got that band. Ti, the integral time based on this table right here, half of Tc will be Tc 100 seconds. So that's it. Based on the inputs, based on the tuning results, critical gain is 5, critical time is 200 seconds, and that is the band, that is the integral time, that's the derivative time. And then you go to your controller, and you set the parameters to the PID controller, and then you will fine-tune it based on the actual results. So if the actual result is a little bit slower, you may increase the gain. That means you change this to, for example, 25. That may increase the gain from 3 to 4. If you find that you need to increase the integral, you lower that number again. The smaller that number, the bigger the integral. Or derivative. If you need more derivative, you experiment, you double that. You double the amount of derivative portion of that control system. So you can control each separately PID. But that is where you start based on the tuning process. So with that, so we introduced 2 methods of tuning. It all depends on your system. If your system can oscillate, you use the second method. Yes, Tim.
Can you show that table again for method?
Which table?
For method 2.
2, okay.
Thank you.
That is the second method called the ultimate cycle method. Second method, cycle method, ultimate cycle. So it all depends on your process. If your process oscillates, you choose your second method. If your process creates this S-curve, you choose the first method. So anyway, so based on how your process perform, you can get the tuning started. Anyway, the final results will all be based on the reality. So these 2 methods only provide guidance because these 2 actually came from experience also. So why is 0.6 over there? Why is not 0.65? Yeah, it all came from experience. This is a very good starting point. Once you have a very good starting point in the field, you can fine-tune it a little bit by varying that from this starting point.
Is that a KP or a KR?
Which one? KP. There's no KR. Proportional gain. KP.
Okay, that's what I thought.
PID control. KP. Yeah.
Okay.
Any more questions? So on Wednesday, we will do the PID tuning using the first method. And then everybody is required to write a summary, project summary. Basically put all you do together as one paper. So we did 3 labs. The first lab, find the range. Second lab, auto-tune. Third lab, tuning with a reaction curve. So what I wanted, I give you 2 weeks till the end of 1 more week. So next Wednesday, that is 1 day after the final exam due. So you have Monday and Tuesday to work on your final exam. Next Monday, next Tuesday, work on your final exam. On next Wednesday, I will try to collect a summary of your project. The summary will include all 3 areas: the range of your controller, how do you auto-tune, and the results of your auto-tune. And then third will be actually we have another one, right? I think we have a 3 and 4. PID parameter, study PID parameter. That was last week, study PID. And number 4 will be the reaction curve tuning research. So all 4, the result of all 4, you put it in one report and upload it to Canvas also. And that will be
Okay, I have some questions.
the majority of your lab credits. Yes. Yes, Joe?
I'm still not convinced I'm doing the auto tune right. Can we go over where things should be set on the controller? Because sometimes I do it and it just runs, and it runs for hours. It'll run for a day, and it never shuts off, and then, or I'll get vastly different values. Like from last week, I ran it twice over the weekend. I got vastly different values than I had the week before.
Okay.
The week before I had like, yeah. So
the auto-tune should end it about an hour, less than an hour.
It's not doing that. It's taken 8, 12. I mean, I've left it all night, several nights in a row. And
After the auto-tune, the controller will just start the switch to automatic mode. So yeah, if you left it on for hours overnight, it will just switch over to automatic mode, PID mode.
Yeah, and I've gotten it to do that a few times, but I'm saying it's just sitting in that flashing now.
Yeah, the flashing is auto-tune. Yeah, when the auto-tune is flashing, yes.
Okay, I'm going to turn here.
So if the flashing for overnight, something is wrong. Yeah.
Well, okay, then I need to know. There's this little light under the run thing on the.
Yeah, that flashing is auto-tune. Yes.
Now, how is that supposed to be set? Can you see that?
Yeah, I can't. I barely able to see. Anybody see better?
It's just a small. The camera is on your screen right now.
I can't see his screen yet.
If you try and click, if you hold your mouse or whatever over his picture, there should be like a little pin there, and you click that, it should put his picture up on the screen.
Okay. Yeah.
Where's it? Right. Anyway, so nothing in the directions tells you where that, what state that should be in.
When you auto-tune, you change it to manual mode and change it to 100%. Must be 100%.
When I do that, that's when it just runs all night and never does anything.
Oh.
I mean, so you're saying go into setting and change it to manual?
For auto-tune, you just go to the setting and go to auto-tune. That's it. I think you did correctly. Yeah. Everything you did correctly, yes.
Okay.
Why your auto-tune goes overnight so long? I don't know. Anybody has ideas?
I don't have any ideas.
I mean, so you remember last week I had like 400 for Kate, for the
Yes.
The initial. Now I'm getting 296, 32, and 8. I've gotten that twice now.
Yeah.
Which seems a little closer to what you got.
Yes. Yes.
But when I do those curves that we did last week, it just runs up to the set point and stops. It's over. There's no error like we're supposed to see. It just, if I set it at 66 degrees, it runs up to 66 degrees and stops.
With proportional only?
Yeah.
With proportional only, yeah, that's maybe because our controller is so, there's no disturbances at all. So another way to get the steady state error is put some load on the system. I mean, drill a hole on your incubator and pull some cold air from your basement. That is the load. You pull a little bit, depending on how much load, it will create error. That's called steady state error. Yeah, I got you, because we don't have a steady state error or a significant amount of steady state error, because our system, there is no load. It's so well insulated. We have a double box.
Okay.
That system is not a real industrial situation where you always have load. So maybe just drill a hole on your incubator and put some cold air through. Yeah.
Okay. All right, so I'll do that because yeah.
The theory is all good, but in practice, there's a lot of scenarios. Yes.
Okay.
In theory, we should have a steady state error because our incubators are so well protected. Yeah, there's no disturbances or load to create that error.
So that'll probably.
So you got a nice basement.
I'm gonna stick with these numbers I've got.
Yeah, whatever number you got is just stick with that number. The number you measured is your system, uniquely related to your system.
Okay. All right.
How exactly do we find the range again? Because I've never got mine to turn off from going too high.
Don't cause a fire. your range is too high. Just turn on manual 100%. Wait for the temperature to stop. That will be your range.
Okay.
So in your case, it may be 40 degree, 50 degree above room temperature. Just keep an eye on it. Don't cause a fire. I guess your heater is so powerful, it might burn through your shoebox. Yeah.
Maybe.
Keep it hot. Yeah. Any questions else?
And finding the range is you can only do that if you know the temperature of the room you're in, right?
It doesn't. It should be independent from the room temperature, but it has a little effect. Yeah.
But you need to know your starting point, right?
Yeah. Finding range, you have to find the starting point. Yeah. When you first turn it on, that will be your starting point, because your controller will probably sit in that room for hours.
Okay.
So that's your room temperature where you start. Yeah. Very good. So on the paper, I would expect 4 sections, each section related to the lab, each lab. We did for 4 weeks. So of course, I would also, if you wanted to add the construction of your box, how do you build the whole system? So that will be 5 sections. So in your lab report, 5 sections. Section 1 will be the construction and the material. Section 2 will be the range. 3 will be auto-tune. 4 will be the effect of PID parameters. Last will be the tuning with the reaction curve. All right, no more questions. I will stop recording. Any more? Any more questions? Every question is a very good question because all of the questions I found not only help me, will help your peers also, because everybody might have same question.
So on Wednesday lab, we gonna do that in class?
We will do it this Wednesday.
Oh, in
That
class.
will be our
right?
last meeting, last Zoom meeting. I will see you guys next spring on Zoom again.
I have a hard time to get on the lab session.
The lab session, yes, I noticed that you are not. I
I'll never be
recorded all the
in
lab
any lab,
sessions.
yeah.
Yeah. Did you see the video lab session?
Well,
Oh, you have a hard time getting lab session? That's a
Yeah.
different Zoom number.
Yeah, I never get in there. Every time I try,
Yeah,
The
I
number-
noticed you were in the wrong meeting room.
yeah.
Go to the Canvas. The Canvas has the right meeting room numbers.
I use that number and it took me to different meeting room.
You have to go to on Canvas. It'll have 2 sections for 452. It'll be like 452-40 and 452-02, and you gotta go to the 02 one.
Okay.
Yes, I noticed he is on the wrong room a couple times, waiting for me, which we are in the lab meeting room. I'm sorry. Yeah, I noticed you were in the wrong room.
That's why I never attend the lab, because every time they tell me I'm in the wrong room meeting.
There's on the syllabus, there's 3 different meetings listed. Yeah.
I think it's 2.
Well, there's one for office hours too.
Oh,
And
yes.
I've had trouble with that. I think I'm getting the right meeting, and I'm copying and pasting the numbers into Zoom, and I end up in the right. I mean, it happened today. I was in the wrong meeting for a while.
Okay.
I'm sorry, where do we find the instructions to auto-tune again?
Instruction auto-tune. It's very simple. Just go through the menu.
Yeah.
Go through the. Do you have the menu with you? That's one-page menu. Yeah.
Hold on, let me put my camera on. You're
Yes.
talking about this
Yes.
manual, right? Okay, yeah.
Yeah, Joe is showing the right one. Yes.
Okay.
Auto-tune is a built-in function of that controller. It just go through the menu, go to auto-tune mode. When you turn it on, it's in PID mode. And then you go through the menu, change to auto-tune mode. It will auto-tune the controller for you.
Oh. Okay. Awesome.
Yeah, looks like most likely our spring semester will be similar, unfortunately, but very confident we'll see everybody in fall.
Wait a minute. So we are having a spring semester, right? Right.
Yes, spring semester is just like fall, this fall. Most likely just identical to fall.
In which we're still going to be over Zoom and everything.
Yes, I guess so. Yeah.
All right.
If we can, maybe we should see if we can do the labs in person.
No kidding.
Yes, that's one way we try. Yeah.
Because all I've got left is the senior project, and I mean, I guess I can do that from home, but you know, kind of weird.
You can
Yeah.
auto tune your PID. That's your senior project.
Right? Yeah. Well, I was going to do a PLC controlled doghouse, with just all kinds of sensors and stuff hooked up to it for scientific purposes.
Oh, that would be pretty cool.
Hope.
Yeah, that'd be pretty dope.
Because I really dig the PLD or the PLCs, but that class got screwed up last spring, and
Oh yeah.
I mean, the second half of that was we couldn't go in the lab or nothing, man. It was
PLD. Yeah, the PLD controller, we can do a PLD on Raspberry Pi. Joe, do you take my Raspberry Pi class?
Yeah.
Yeah. Open PLD, that works actually.
Yeah, I saw that. I was considering. I've got a buddy who he has some PLC controllers laying around. He's going to give me. But it'll just be, which one's easier to get. Once I get this video game thing done, my brother may not give it back to me. I have to buy another one.
Yeah, another $35.
I bought the expensive one.
All right, I see you guys Wednesday, and
Okay.
Yep. See you Wednesday.
yeah, bye.
All right.
But
See you guys.
Later, guys.